the amino acid it carries is added to the growing protein chain. Again, you are watching this in real time. And after a few seconds, the assembled protein starts to emerge from the ribosome. Ribosomes can make any kind of protein. It just depends what genetic message you feed in on the RNA. In this case, the end product is hemoglobin.
So we're basically a machine. The ribosome is a machine. Sorry about that. And it works based on the code coming in. It's like a tape. Comes in, reads it off, brings in, bing, bang, boom, transfers it, and just translates that coded message and the codons of mRNA into basically a protein, a polypeptide. Okay, and that's what it's all about. Yes?
So based on the code that comes in, like it decides which protein that is, and it like pushes that out.
It determines what protein is. Yeah, the gene, the sequence of DNA creates a transcribed message of mRNA that's translated into the protein that was coded for on that DNA. So that's the link. Okay? Now, I'm going to show this one more video other than this.
A transfer RNA molecule is composed of 70 nucleotides. Each transfer RNA molecule recognizes only one amino acid, which becomes bonded to the top of the transfer RNA molecule.
Things down a little bit.
Located on the bottom of the transfer RNA molecule are 3 nitrogen bases called an anticodon.
All right, so if you look at this is kind of slow. So if you take the tRNA, up on this end is going to be one of the 20 amino acids, right? And it corresponds to the anticodon here, and that anticodon is spelled out. This is fixed. These are us floating around there. And then what they're waiting for is the ribosome to expose its mate, which is basically the codon. What would the codon be for this? This is a U, by the way. A, U, G. So if you have an exposed message like that on the mRNA, this guy is fair game to bind to it. And what it does, that amino acid just gets transferred. And I'll show you that in a second.
That pair up with messenger RNA codons during translation. As translation begins, the first codon of the messenger RNA strand attaches to a ribosome. Then, transfer RNA molecules, each carrying a specific amino acid, approach the ribosome. When the transfer RNA anticodon pairs with the messenger RNA codon, the two molecules join. Often, the first codon on messenger RNA is AUG, which codes for the amino acid methionine. AUG signals the start of protein synthesis. The messenger RNA then slides along the ribosome to the next codon, where a new transfer RNA molecule carrying an amino acid will pair with the messenger RNA codon. The two adjoining amino acids then become joined by a peptide bond, and the first transfer RNA molecule is released by the messenger RNA. As the process continues, a chain of amino acids is formed until the ribosome reaches a stop codon on the messenger RNA strand.
Make sense? Okay, this one really does put it together. Yep. Yep. The first one I just want to show you the world. All right. So, go ahead.
When it's A to T,
It's not.
when it's A to T instead of A to U, is that in the making of like DNA?
You will see no T's in RNA. So
So if it says RNA, just don't use the T at all?
Yep, there's no T's.
Okay.
Okay? So the only time you'll see T's is in DNA.
Okay.
And that's one easy way of chemically deciphering which is which. Okay? And okay. So let me just recap that again. Hold on, Lauren. I'll go through. Okay, so just see if this makes sense, a little more sense now. We go through the steps. Okay, so here we go. mRNA attaches to the ribosome, right? The TNA with the corresponding anticodon attached, recognizes that codon. The amino acid that is on it it's on the chain, starts the chain. The first one would be the start signal, and everything afterwards just gets tagged to it, attached to it. Next, it slides along. Next TNA binds to its corresponding anticodon-codon, continues along. The amino acids are formed by a peptide bond. There's enzymes actually to do that too. Obviously, we're not worried about those guys. And this continues all the way along the chain from start to stop until the entire gene is coded for. At which gets a stop, the ribosome falls apart. Got a polypeptide protein. That's translation. Okay. Taking the mRNA, converting it into a polypeptide. All right.
So technically, if the sequence never really ended, like for a long time, we'd have a really long polypeptide sequence.
Yeah.
Is there a certain amount?
Yeah.
Where it's like
Some proteins, particularly enzymes, because they're so complex, way back when they're like they get to a real globular form, they tend to be longer. And some proteins are so yeah. Depending on the complexity of the protein and the length, the process can take much longer. And obviously, the mRNA is longer because the protein's going to be longer, and so the strain of the DNA is going to be longer. So yeah, it's all kind of correlates. Okay, shoot.
How do they determine like which amino acid they're gonna make? Like if it's gonna be glycine or glutamine. How does that like?
Well, the amino acids are things out there that we know. It's kind of like the elements of the periodic table. They make up all proteins, so those are just the units of proteins. And so where do we get those from? And that was getting back to, we kind of talked about this, essential versus non-essential. Essential, we can kind of make them ourselves, a whole different process, or we have to eat them. And when we eat them, we break proteins down that contain these things and go, and digestion breaks those proteins, polypeptides, back down into the individual parts that get bound to tRNA to re-put together into the proteins that we want. So
we use the amino acids to make the proteins.
Yeah, we use amino acids that we eat that are broken down through digestion for our own synthesis of our own proteins. Absolutely right.
All right, thank you.
Yes, yes.
okay, so you have your DNA and then your genetic code, and then the mRNA, all that comes along and takes it and it goes and then makes the polypeptides
Yep.
essentially from the DNA that
Yep.
you already have.
Yeah, the DNA, mRNA to polypeptide. It's kind of this.
So that's like proteins, and that's
Yep. Yep. And we're going to recap that in just a second. Oh, so anyway, so real quick, this is more what it really looks like. Here's the anticodon again. Here's the codon, anticodon recognition. We already saw there's one amino acid on the end. Again, go through this. There's a ribosome. Here would be the peptide bond forming, just so you know what a peptide bond looks like. You'll maybe, I don't even know if you probably won't touch this next year. It'll be like maybe AP chemistry and what you get organic chemistry. They'll show you how that works. Essentially, you're taking water out, who cares? But that's what a peptide bond is for your information, okay? And here's the growing string of amino acids and showing the basically different sites that are exposed. And again, it's kind of a better. So let's do this. If you have, and we're going to do this on your piece of paper in a second, so don't you have to write this down because you have this. And we're going to do this. If you have an mRNA strand like this, okay, notice the AUG. You go down here, the first base of that codon, remember we read it in threes, triplicate threes. A here, U here, so the A and U puts you in this quadrant, I guess. And then the third one is G. Because you're in this quadrant, you go look here for the G. You follow along, and here we go, methionine, start codon. Every living thing on the planet works this way. Everything's made up of those 20 amino acids. Everything shares the same code. So we can take this for a bacteria and do the exact same thing. In fact, that's what science has been doing for probably 20, 30 years now. Isn't that incredible? So let's go ahead and do the second one. Do the second one. Put your hands up. So that one is CGU. So you guys see, you can look on this or on your paper, the same one. You can see that better. C, G, arginine. And normally they abbreviate them because they're just easier to write out. Okay. And then it continue down. So if you do this, methionine, arginine, serine, and then where's the last? Oops. UGU, what?
I'm kind of confused on how.
I didn't get on this. On this it says AUG.
Ah, stop codon. Very good.
Ours is different. Ours is different.
Yeah.
The first.
Yes. Yes, yours is different. This is an example. That's what we're going to do in a second. I just want to show you how to do that. All right, so now, listen up. If you have DNA, you should be able to go and make the RNA strand, right, which is what we did, and And then you should be able to use that to actually come up with the amino acid string or the polypeptide. So that's what the expectation is here. So let's go ahead and do this on your paper because we're running out of time. All right. So grab your protein synthesis handout, everyone, and just practice some protein synthesis, shall we?
Let's do it.
All right. So the other day we went ahead and transcribed this puppy. You should all have that done. Do you want to?